Vojnovic, that we talk about the generalized solutions to differential equation with finite method.
First, I would like to thank the organizers for being here. I'm really glad to be here. And the beginning of my talk will be on the blackboard. So I will start writing, and then at some moment we will see slides. My talk is about so-called generalized solutions to differential equations, which is one way to deal with singularities like delta distribution. Because it's known that, I don't know, for instance, in solving equations, we occur problems like what is delta times u? Delta is standard delta distribution, and for instance, let's say u is an h. So what is meaning of this expression? Or what is delta times delta, and so on. So what is known in distribution theory is that we can multiply distributions with smooth function. And that works easily. So for instance, let's now assume that u is in d prime Rn. I will just give a quick reminder. So this means that u maps space of smooth compactly separated functions to, let's say, complex field. And it's linear, mapping, and continuous with respect to topology in this case. So what is well defined is if we have fu acting on some test function phi, so f is in C, phi is in C. I will stop writing that because we assume that we have whole space. So this is defined to be u f times phi. And it's easy to prove that the definition makes sense. It's fine. So in this case, we don't have problem. But very soon we come to examples which show that there are serious limitations if we want to multiply any two distributions. So for instance, first example, let's say we have delta, and we have so-called principal value distribution, which acts in phi as integral from 0 to infinity, phi x minus phi minus x over x, it should be x. And now, what is possible? So, for instance, let's first look at this expression: delta x times principal value distribution. So delta x when it acts on phi. Okay, so x is smooth function. In this case, that's well defined. So it will be delta acting on x phi multiplied and 0 will be 0. So okay, this will be 0 times some distribution and 0. On the other side, if we observe x times principal value acting on phi, okay, again, smooth function, it will be x phi. And then when we apply this definition, here it will be x over x. In the end, when we calculate this integral, it will be actually 1 acting on phi. It will be just integral 1 phi dx. So this, now when you look like this, delta times x times principal value, this is 1, so delta times 1 is that. So what we see? Here we got zeros, here we got delta, so obviously associativity doesn't work, which would be natural assumption to multiply distributions. So, okay, this is simple example. We already see that we run into problems. So let's see another example. So what will be the aim in the end is to embed, let's say, this D prime into some algebra, multiplicative algebra A. let's say that I is this embedding, so we want to achieve then something like this. To have some bigger algebra and our B prime embedded inside. And then in this way, we want to achieve that products like this get sets by embedding them into some bigger structure, which has reasonable definition of the multiplication. Okay, second example. Now, what would be reasonable requirements for our algebra? How to construct algebra? So, for instance, okay, let A be, so what are reasonable expectations? A to be associative, commutative. Algebra with derivation, so we also want to have derivatives included. We want differential algebra with derivation and satisfying Leibniz rule. Okay, so then what we will do? Then any element, let's call it H of our algebra, with property H times H is equal to H must be constant. That is, it must hold that H prime is zero. So if we want any non-zero element with this property, we must have the derivative of that element is zero. How to see this? Okay, we assume the Leibniz rule, I mean standard rules of derivation. So H square prime will be 2H H prime. On the other side, from H times H equal to H, we obtain that H is equal to H square is equal to H squared. On the other side, when we look at H third prime, it's 3H squared H prime. And then what do we get from here? We get that 2H H prime is H square prime, H square is H, so 2H H prime is H prime, and it's equal to 3 H. And then from here, it's clear that H prime might be 0, and then H prime must be 0. Okay, so this is relatively simple to show, but then in our case, if now H is Heaviside function, which we can consider as distribution. So if we have algebra, we want to embed distributions. Let's say that H is Heaviside function. Then, okay, H times H is H, we can be satisfied. And then what we cannot have, we know that H prime in distribution theory is done. But this example tells us, okay, we need to give up because H prime must be 0. So, these all examples will lead us to assumptions on algebra might be satisfied, so we can achieve embedding of spatial distributions. Okay, so let us now collect what we got. So what would be reasonable requirements for our algebra? So we want to embed the prime into some algebra class. And the question is it possible? To construct commutative associative algebra. Calculate. We have, again, the derivations of values will satisfy. So first requirement, so the plan is with embedded. Okay. Then second requirement, we have derivations VI. Okay. Which are linear and satisfied. Third requirement. Okay, we want, when we do restriction to D prime, we want restriction of derivative to be this distribution. So when we restrict derivative to D prime, so we want this to be derivative. Usually in the sense of distributions in this case. And fourth requirement, which is also natural, when we restrict multiplication to, let's say, an infinity or a lot of infinity, we want it to be standard point with. So this way. So this is like, let's start with the biggest space. Let's say infinity walk. Coincides with the pointwise problem. Okay, but what this example, previous example to show us, we had we assumed first two requirements, but then we see from this example that 3 and 4 cannot fall at the same time in this example. So obviously, this is too much to expect. And then idea was, okay, let's restrict this pointwise derivative to continuous functions. So C times C. But there is a Schwarz impossibility result that tells us that there is no commutative associative algebra satisfying these first three rules, and rule number 4 with replaced with continuous functions. So we cannot expect continuous functions also here. So if we want to replace 4 with, say, 4 prime, then we have Schwarz impossibility, which tells us it's not possible. Also, it's not possible if we replace it with CK times CK for any K in M. So if we increase regularity, it's still not going to work. But surprisingly, C infinity works. So we will replace condition 4 with 4 seconds. So it will restrict our multiplication to C infinity times C infinity. And then requirements for algebra will be first 3, and that multiplication of smooth functions coincides with pointwise. Okay, so now let's see. Question is okay. we will try to construct this, but still we don't know what will be our output, so how to construct. What helps with this is sequential approach to distribution theory. So now we will see one theorem which actually gives us another characterization of space D prime using the limits of distribution sequences. Okay, let's say we have E from 0 to 1. Let's observe maps of functions U epsilon, where epsilon belongs to I. So we will define set mu, let's say mu, to be set of all U epsilon nets from C infinity. So U epsilons are belong to smooth functions infinity, such that there exists U in D prime, so that limit of U epsilon is U. This means that U epsilon tested on pi equals to U pi epsilon. So this is the first space we define, and then U0 we define to be again space of these nets. But this time we assume that nets converge to 0. And okay, obviously mu0 is subspace of U. And we can look at factor space mu over mu0. And then there is theorem that says that linear map that's denoted by type from this factor space into D prime. Okay, so here we take epsilon plus mu0, and we will map it to distribution U, which is actually because this U epsilon is from U, which means that it has limit in D prime. So we will naturally then map this into limit U epsilon. We know that it's a distribution D prime, and then this mapping is an isomorphism. So this gives us another characterization of D prime. And okay, let's see it through, because it is simple and it will give us idea of how to embed distributions. So okay, injectivity is easy, so I will not go to it. I mean, it was very directly and reveals nothing more essentially but subjectivity. For instance, if we take U in D prime, what we want is to get some sequence U epsilon, some net U epsilon. So what are we going to do? We will modify U. So we will say, let's say that U epsilon is U star rho epsilon. Where, okay, rho epsilon is in CC infinity. Then how we construct rho epsilon? We start with rho CC infinity such that integral of rho is 1. And then we say that rho epsilon of x is 1 over epsilon to n rho x over epsilon, then this convolution will be in infinity. So u epsilon will belong to this space, and we know that limit of u star epsilon is u. So we have substituted. And this is important point now because we will use convolution of the distribution with appropriate modifier to embed distributions into our algebras.
So what we show, what is the topology of mu in subclass of zero?
Yes, it's topology of factor space, but just a second. This is just proof of this activity. Yes, no, you are right. I am not going into, when it comes to continuity, I will not discuss because I didn't introduce topologies from the beginning on all these spaces. So I just want to give a short overview. But you are, I mean, continuity is separate. Thank you. Okay, and now. Okay, we will start. First, what we can observe is that this space of nets is differential algebra. This is not hard to see. And then we want to embed the prime into some differential algebra. So, okay, what we will do now, we essentially will use that the prime can be used, written as this factor space. So now, okay, choose some, so now we will need bilateral idea in this C infinity, choose some, yeah. Okay, let's denote this. C infinity, such that I is subset in mu0. So what are we going to do? We are going to embed d prime into this C infinity over our idea. So we need this to be ideal in order to ensure that factor space is out. And what are we going to do? We will make distribution u into u star rho epsilon plus our idea. Rho epsilon is the same as what? And question is now how to reasonably, how to choose this idea. So what would be reasonable? Also, what we want is that when we restrict multiplication on smooth functions, so this is factor space. No, this is nets. This is this index set up. Maybe.
The nets, like you call it u epsilon epsilon in this relation. It's a space of nets.
Okay.
It's a Cartesian product.
Yes. So these are just nets. This is index set.
It was being this flash was in this space then.
Yes.
Before. This
What about it?
This I and the
Ah,
Y
okay,
seems the same.
Yes, yes. Okay, thank
Of the same line.
Okay, so, yes, we want multiplication to points and smooth functions. So what would that mean in this setting? We want this to be achieved. So, of course, in this Gaussian spaces, we define multiplication of classes and addition in standard ways. We hope. So what would be, so if we have MG in C infinity, then, okay, F star rho epsilon times G star rho epsilon, we take photo, plus I, we want it to be MG star rho epsilon and plus I. So how to choose our ideal I, so we ensure that this holds, that we have a restriction of C infinity to be a point. And then, what is main observation? If we have any F in C infinity, natural way to embed it F into our algebra would be, because here already nets with the elements which are smooth. So natural would be actually to do this. Sorry, I mean to just use it for each epsilon to give it F because it's already small. But on the other side, F star epsilon plus R. Okay, so here is this. So what would be good? That difference of these two belongs to our ideal one. And then if that is achieved, if we can choose our ideal I, so that F star rho epsilon minus F belongs to our ideal, then we will also ensure that this property. And then here, idea is just to use Taylor theorem to expand this. I mean Taylor expansion, and then okay, I will just write what we get after expansion, because then we will see how to define this and this. Some integral sum k m minus epsilon by k to the k factorial I dr plus this integral m is a function of numbers, so m plus 1 and plus 1. In this we have the plus 1 factorial f n plus 1 derivative by dy. Then we will use one more assumption on our this modifier law. Now we will say that we will be cross such that integral Rm of rho of x xk dx is 0 for all k greater or equal to 1. And then this will give us estimates. So we want this difference to belong to ideal I. So if this part we can exclude because this integral is 0, we will have no y to k. Then from here we can come to definition of our ideal. So which kind of estimates are going to be satisfied for nets that belong to P. So we come to and one more thing, yes. I started with infinity over I. And then, okay, we have this idea of I, but it turns out that this algebra is too big because in C infinity can be sequences of arbitrary growths over 1 over epsilon. So we will actually take a subset of this space and ideal according to this here expansion. So definition will be like this. First, we will define epsilon and s to be set of all nets such that for all compact case beta, for all multi-indices alpha, there is some n to n such that supreme x over k, the alpha u epsilon x is before epsilon minus n. And we call them sequences of moderate growth. And then we will define our ideal I. We will denote it by n s to be set of nets u epsilon. Again, C infinity. It such that for all compact case, for all alpha, we have that supreme over k, the alpha u epsilon of x is before epsilon to the power of m, also for all m. And this estimate we derive from here. So motivation for this estimate comes from this Taylor expansion. When we wanted to ensure that this difference will be in ideal, so we call this I now negligible nets, and we had to take subset of this big algebra from the beginning. So we took not all C infinity nets, but we took nets of moderate group. And then we construct algebra as factor space. So we denoted T as defined to be EMS over MS. And this type of algebra we go for algebra. So we will deal from now on with algebras of this type. And this S is superscript for so-called special form of algebra. This is just one example. So depending on which equation you're trying to solve, these definitions can be different, but the idea is still the same. We always deal with sequences, I mean, nets of moderate functions and nets of negligible functions. Okay, now we will switch to example of solid shredding. I mean, a hard equation, regular equation with hard type nonlinearity within this set. Maybe now. Okay, so first, let's say that started type equation with non with this singular part, so we have delta u, and u of 0 x is the x. And okay, depending on this initial condition, so because we're asking the sigma A will be H2 or L2, we will see. And then this special type of algebra is not so suited because here nets are in C infinity. And our initial condition is not going to be in C infinity. So we will have to tailor algebra in a way that we can apply this theory. But also, we will see soon what does it mean to solve this equation within algebra. So essentially, we will find we will have a set of equations. So for each epsilon, there will be one group epsilon. Delta will be modified with rho, with rho epsilon. So then we can deal with delta. We can find solution within algebra, and solution will be actually in this factor space. And then what we will show, because solution will be okay, some net u epsilon plus this ideal. But what we will show is that in some cases, this u epsilon that we get as part of algebra actually can converge in some sense to strong, let's say, classical solution of our problem. Of course, not with delta, but for instance, when we don't have delta, and here is 0, we will show that this net that we get actually converges to classical solution. So that's the next part.
It seems that this, from this point of view, you don't know the dimension.
No, for now, this is general.
With the delta, it should be.
Yes, yes, of course. Later it's very important. Okay, so another thing is what is also important. Here I didn't say, but when we want our modifier to satisfy this additional condition, then we actually need to restrict ourselves to space of rapidly decreasing function without CC infinity. So rho cannot be any more than CC infinity. And then we need to be very careful with convolution, because if we take any u, any distribution, and convolve it with object in S, we need to be careful what is going to be. But in our here examples, we will do the only one singular object that makes us problems is delta, which is actually compactly supported distribution. So convolution with S will make sense. But so there are some limitations here, but they are not going to affect us. So I would like to